We're going to work on an ALEKS problem that deals with calculating an equilibrium constant from a heterogeneous equilibrium composition. This is an example of a heterogeneous equilibrium, and this is just an equilibrium that has components in more than one phase. So we have components in the aqueous phase, and we have components in the gas phase. The equilibrium constant expression is derived from a balanced chemical equation, so the reaction has to be balanced, and the equilibrium constant expression is capital K is equal to the concentration of the products raised to the power of its coefficients over the concentration of the reactants raised to the power of its coefficients. A couple of things we want to remember. The bracket symbol means concentration, which means molarity, moles over liters. And this equilibrium constant expression excludes any component in the solid or liquid phases. So we don't include any reactant or product that is in the solid or liquid phase. Let's take a look at an example. In this example, iron and water react to form iron 3 oxide and hydrogen. They give us a balanced chemical equation. They also give us a table with the different compositions of the different components. And they also tell us that this reaction is in a 6.1 liter vessel. They are asking us to calculate the value of the equilibrium constant for this reaction, and they want us to round our final answer to 2 significant digits. The first thing I want to do is come up with an equilibrium constant expression, which is capital K is equal to the concentration of the products raised to the power of its coefficients over the concentration of the reactants raised to the power of its coefficients. If we take a look at our products, our product has iron 3 oxide, which is a solid, so I don't include that, and hydrogen gas. So K is equal to the concentration of hydrogen raised to the power of 3 over, take a look at our reactants. Iron is a solid, so we don't include that, but we can include the concentration of water raised to the power of 3. Now, concentration means molarity, so I'm going to write that down so I don't forget. Molarity is moles over liters. So they've given us the composition in grams. I'm going to have to convert my grams to moles, then divide that by liters to get the concentration. Now, I'm not going to do all of the components of this reaction because I don't need to do the ones that are solids and liquids. So I'm just going to focus on what's involved in my equilibrium constant expression. So let's find the concentration of water. I'm going to convert 1.15 grams of water to moles. And I'm going to divide this by the liters to give me concentration. I'm also going to find the concentration of hydrogen. And I'm going to divide this by liters to give me concentration. All right, I have my concentrations. I'm going to go ahead and plug that into my equation. And I want to remember that my final answer needs to be in 2 significant digits. So I'm going to take a look at my second significant digit, look at the number next to it. If it's 5 or more, I have to give that underlined digit a score. This is a large number, and I need to show this large number using only 2 significant digits. So I'm going to have to use scientific notation. So my final answer is K is equal to 1.2 times 10 to the 4th, and K has no units. Let's take a look at another example. In this example, methanol and oxygen react to form carbon dioxide and water, and they've given us a balanced chemical equation. They've also given us a table with compositions of the different components, and they tell us that this reaction is in a 3.3 liter vessel. They want us to calculate the value of the equilibrium constant K for this reaction and make sure to round our final answer to 2 significant digits. So the first thing I want to do is come up with a equilibrium constant expression, which is the concentration of the products raised to the power of their coefficients over the concentration of the reactants raised to the power of its coefficients. So take a look at our product side. We have 2 components that are in the gas phases, so I have to include both of those. And then over my reactant side, on the reactants, methanol is a liquid, so I have to exclude that, not include that one. And I take a look at my oxygen and raise it to the power of 3. And again, I want to remind myself that concentration means molarity, which is moles over liters. So I'm going to have to convert my components that are in grams to moles and then divide that by liters. So let's start off with the concentration of oxygen. And I'm going to divide that by 3.3 liters. And then I'm going to go ahead and find the concentration of CO2. And divide that by liters. And the concentration of water. Divide the moles by liters. Okay, so now I have all the concentrations I need. I'm going to go ahead and plug this into my equilibrium constant expression. And this gives me a very small number. But I want to round my final answer to 2 significant digits. So I take a look at my second significant digit, look at the number next to it. Since it's less than 5, I keep my underlined number at rest. So my final answer is Kc is equal to 0.0017 and no units. Good luck and keep practicing.